Okay. So, okay, last Thursday we were watching this video. This video was about, it's a third video in the subsonic compressible flow topic. And what we were, just to remind you, I would like to remind you where we were. What we were talking about is, I mean, like we did last semester, right? If you guys remember last semester, what did we do? We were trying to analyze subsonic flow. But we were trying to analyze, we focused on subsonic incompressible flow last semester, and we obtained, I mean, we introduced the potential function last semester, and we obtained the governing equation, the potential equation for subsonic incompressible flow, which was the Laplace's equation, if you remember. And that equation is a linear second order partial differential equation. Since it was linear, we were able to define certain fundamental flows based on certain fundamental potential definitions, and we were able to just add them up. So just add them up and obtain more complicated flows, and even extend that methodology to just a second, I keep getting some messages from Rector in the meantime. Anyway, extend this to numerical methods like panel method and everything. So that's what we did. The thing is, right now we want to do the same thing, or maybe I should say similar thing. What do we do? We would like to obtain a solution using potential function, but now for subsonic compressible flows. Subsonic compressible flows. So for that, we started doing that. We obtained an equation. In reality, we watched the video. I also tried to explain it, and we obtained an equation. However, that equation is not, it does not look anything like the Laplace's equation. First of all, it's not linear. So, so this means that I mean, it's quite challenging to obtain an analytical solution to that. So, I mean, with numerical methods, you can of course solve it. But analytically, it's not that straightforward. So if you would like to have an analytical solution, then what you need to do in mathematics, if we have nonlinear equations, and if you would like to have analytical solutions to any nonlinear equation, one approach is to linearize the equation. And one method that we use in mathematics to linearize nonlinear equations is a method of perturbations, basically, small perturbations, I must say. So what do? We say we introduce certain conditions. That conditions, I mean, we say this. Okay, look, this is our. Okay, we understand this is a, complex nonlinear equation, but maybe under certain conditions, this equation could behave like a linear equation. What are those conditions? So under the conditions that the main variable, main dependent variable is changing a little bit from its, let's say, baseline value. So what we did is, this is called small perturbation theory, and basically we apply it to our potential equation. We said, well, small perturbations can be relevant to aerodynamics. How? If it's, for example, if there is a free stream flow with no disturbance, if there's a solid object immersed into that flow, and if that solid object is disturbing the flow in a small fashion, meaning that disturbing the flow, what do we mean? Small disturbance to velocity components. U velocity component will change a little bit. V velocity component will change a little bit. Maybe pressure will change a little bit. So under those conditions, can we actually linearize? I mean, can the equation actually be linearized? And we did that, and it is indeed, it can be linearized. And in fact, we took it further to obtain, for example, an expression for the pressure coefficient distribution on an airfoil like that. Of course, it needs to be a thin airfoil, because we do not, we only limit ourselves, or we only limit the solution of this equation to small perturbations, the airfoil should be thin, so it's not going to disturb the flow a lot, meaning it's not going to generate high, high magnitude changes in velocity components or pressure. So under those conditions, we obtained an expression for pressure coefficient, which is where we left actually. It was the last thing we were talking about, Cp. And Cp written, as you can see here on your screen now, written as a function of, so it's -2 times u hat, which is the perturbation velocity, so small difference from, let's say, v infinity divided by u infinity. So it says that this equation will give you your pressure coefficient around a thin airfoil for a subsonic compressible flow, and that by satisfying the linearized potential flow equation. So that's where we left. So we'll continue from there. As I said, I can stop and make more comments. And if you have some comments or if you have some questions, please interrupt at any time. We will discuss, okay? Anyway, let me first go to full screen and let's start it.
Hocam, I guess we cannot hear the sound.
You cannot hear, I guess. I have to reshare it again, just a second.
Equation that I showed a couple of slides
Can
earlier.
you hear it now?
Yes, sir.
Then you can easily calculate this pressure coefficient, and then you can then integrate this pressure coefficient in order to get lift and moment coefficients. But okay, while you are solving that equation, that's the equation that's shown here, which is, okay, let me go back, which is this one. In order to have this solution, you need to, of course, apply some boundary conditions, especially at far field and at the wall of the object, at the surface of the object. So first of all, at far field, we may safely assume that our perturbation velocities goes to zero at infinity. So which means that your perturbation velocity potential, which is phi hat, should be constant in that case. So if your phi hat is constant, the phi hat over dx would be 0, and or the phi hat over dy would be 0, which means that your perturbation velocities would be 0. And now let's look at the solid boundaries. And at these solid boundaries, because we assume that the flow is inviscid, there has to be flow tangency condition still applicable. So which means that the tangent of your surface should be parallel to your velocity vector at any point on the surface. This can be represented by this equation here. Your tangent theta, that's the theta here, is the tangent theta is the tangent of your let's say surface, should be equal to v over u, and v once represented in terms of the perturbation velocity, it's directly v hat, whereas u is v infinity, which is the free stream velocity, plus u hat. And of course, when you compare these two terms, you can easily say that v infinity is much larger than u hat, so that you can neglect this second term here, which will bring us to this final relation. V hat is equal to v infinity times tangent theta, and v hat is d phi hat over dy, of course, and that's equal to v infinity times tangent theta. Okay, when you apply these boundary conditions and get a solution for phi hat, then you can easily calculate u hat and v hat, and once you know the u hat, then you can calculate the pressure coefficient as shown here. Okay, so now let's look at if there is a kind of an easier way to calculate the pressure coefficient in compressible flow if you already know the incompressible flow pressure coefficient. So let's start from the beginning. In aerodynamics 1, we set in the thin airfoil theory that for incompressible flows, which is for Mach numbers smaller than 0.3, we may assume that the variations in density are negligible, so that we assumed it's constant, and we ended up with some, you know, some equations, and once they are solved, we calculated pressure coefficient and some other forces and so on. Now let's look at what happens at if the Mach number is greater than 0.3. Of course, then the variations in density cannot be neglected in that case. So then we need to then apply some corrections for these variations in density. And the first method to perform such a correction is Prandtl-Glauert correction method. It's completely based on our linearized perturbation velocity equation that we derived a couple of slides ago, and which means that then this correction is only valid for thin airfoils at small angles of attack. And also, this correction method works only up to Mach number 0.7, and for greater values of Mach number, it deviates from the experimental data. So it's only valid for subsonic flows, and particularly smaller than 0.7 Mach number. Okay, so the derivation of this correction method is rather simple. It's mostly based on it's mostly based on a transformation from our physical space of xy coordinates to some other space, which I'm going to explain on the slide. So let's consider this airfoil shown here, and the shape of the airfoil is defined by a function x, y equals to some function of x, and we have, you know, u component of the velocity, that's v infinity plus u hat, and you have the y component of your velocity, that's directly v hat, and of course you have the flow tangency condition here. This angle theta is also the angle of the surface at this point. Okay, the angle of the tangent of the surface at this point. So let's use our linearized perturbation velocity potential equation. So it's actually given as 1 minus Mach infinity squared d squared phi hat dx squared plus d squared phi hat over dy squared. It kind of resembles, to some extent, well, if you don't actually consider this term, it kind of resembles the Laplace equation, but it's not the Laplace equation, of course. So let's see if we can find a relation with the incompressible flow with the Laplace equation if we apply some transformation. That's why we apply here some mapping from our xy coordinate system to some other coordinate system. Let's start with defining beta square, which is 1 minus Mach infinity square. So once defined, the perturbation potential equation becomes this one shown here. And now let's apply a transformation from xy coordinate system to psi eta coordinate system, such that this psi equals to x, eta equals to beta times y, and then you can actually calculate also yourself the psi dx, the psi the psi dx, the psi dy, the eta dx, the eta dy for these mapping relations. Once you have these calculated, now let's look at how the derivative of phi hat, that's the perturbation velocity potential in physical coordinate system xy, is related to its derivative with respect to psi in the transformed space. So let's look at the phi hat over dx. First of all, it's actually d phi hat over d psi times d psi over dx plus d phi hat over d eta times d eta over dx. So it's basically we are basically using the chain rule here, and as d eta over dx is 0, we end up with d phi hat over d psi here. Likewise, if you do the same thing, d phi hat over dy would be equal to beta times d phi hat over d eta, which is shown on the right hand side of this slide. Okay, we'll continue in the upcoming video.
Okay, just a second. Any questions up to this point?
Hocam, what is the physical definition of these Greek letters for over the airfoil?
You mean which ones? Beta, eta, psi? These
Eta
ones?
and Xi.
Eta and psi. So basically, let me explain it again, Melih. Just a second. You can hear me? But I lost.
We can hear you, but we can't see your screen right now.
Just a second. I lost my Zoom screen. Let me share it again. Sorry, I have to redo it. Okay, so you can see the screen and you can hear me?
Yes.
So, okay, basically what we are trying to do is this. So we have the linearized potential equation, yes? You see it here.
Yes.
So the thing is, this equation is not Laplace equation, right? And we know that for incompressible flow case, the potential function or the potential field is governed by Laplace's equation. And the question is, can we actually get a relation between this equation, which is the linearized version of the linearized form of the potential of the differential equation for the velocity potential, and between this equation and the Laplace equation, because Laplace equation is the governing equation for incompressible flow. Why am I doing this? Because I'm doing this because of the fact that I do know how to solve incompressible flow potential equation, Laplace equation, which we learned last semester, right? And we actually learned, for example, how to calculate pressure coefficient, right? Starting from that point for incompressible flows. So the idea is, if we can relate this equation to Laplace's equation, we can maybe estimate also, for example, pressure coefficient for compressible flows based on the pressure coefficient for incompressible flows that we obtained through the solution of Laplace's equation. Okay, so I mean, we will, if this airfoil is given to you, what you could do in the hypothesis is this. What you could do, or what the proposition by Prandtl and Glauer is this: if somebody gives you this airfoil, just solve the just obtain an incompressible flow solution. How? I don't know. Use panel methods, yeah, or use, you know, combine some fundamental potential solutions. Just obtain an incompressible flow solution around this airfoil, which will give you the pressure coefficient, for example, also on this airfoil. But we know that, I mean, if our main problem is to obtain what would be the pressure coefficient if the flow was compressible rather than being incompressible around this airfoil. So the idea is that let's obtain it first for incompressible flow, then let's devise a methodology to correct the value that we get for the incompressible flow. So did you get this idea first of all?
Yes. So you basically trying to implement incompressible flow equations to compressible flow.
Right, but the governing equations are different. The governing equation is here. As you can see, the perturbation equation is not the same as Laplace's equation. So the question is, by applying a mathematical transformation to coordinates, can I actually make it look like a Laplace equation? Meaning that I can, instead of x, I can define another parameter psi. Instead of y, I can define another parameter beta times y, and beta is this here, 1 minus m infinity square. And then instead of x, and derivatives with respect to x and derivatives with respect to y, I can get derivatives with respect to psi and derivatives with respect to eta. So I can obtain a transformed version of this equation. Okay. So the so psi and eta, these Greek letters, are just transformation. We are transforming from xy coordinate space to psi eta coordinate space. This is just a mathematical transformation, hoping to get some, hoping to relate this equation to its incompressible form. Okay.
So psi is equal to x, but eta doesn't represent any physical phenomena, right?
No, and both of them represent physical phenomena. Psi is equal to x, eta is equal to beta times y, right? Beta is just 1 minus m infinity square. Beta square is 1 minus m infinity square. So beta is square root of 1 minus m infinity square times y. They do represent some physics, but they are not our actual physical coordinates, of course. They are just mathematical definitions to transform the equation.
Teşekkür hocam.
Hocam, are we trying to get rid of the beta square for in this equation for doing this transformation? Since
let's see how it works out. Okay, let's watch and let's see how it works out. Let me start.
Okay, now we have described the mapping relations from our physical coordinate system of x and y coordinates to some other space that's psi and eta. Now after this step, let's also define a new potential field that's represented by phi over bar, and that's actually equal to beta times phi hat. That's our let's say that's our perturbation velocity potential defined in our physical field. Okay, so after defining this, one can also get the derivatives of this phi hat with respect to x in terms of the new potential field, and in the transformed domain. Well, you can actually get these relations calculated by yourself quite easily, I assume. So of course we look at the first derivative and the second derivative relations, because at the end we would like to represent our initial potential velocity potential equation in the new transformed domain. So that's actually here beta squared times second derivative of phi hat with respect to x, and second derivative of phi hat with respect to y. So now we have the corresponding terms in the transformed domain in terms of the new potential field, and then if you replace these into this equation, then the new equation becomes a second derivative of phi over bar, which is our now potential field in the transformed domain with respect to psi, and plus second derivative of phi over bar with respect to eta, and summation of these two equals to 0. Now this equation should look quite familiar to you, because this is nothing but Laplace equation. So we started with our, let's say, velocity potential equation that's defined for compressible flows, and we applied some transformation to another space from xy coordinate system to psi eta coordinate system, and then in this psi eta coordinate system we have defined a new velocity potential field that's given by this relation, and we ended up with Laplace equation. So which actually states that the flow in the transformed domain, this part is important, the flow in the transformed domain is incompressible. So in our physical domain it's compressible, but after we map it to another space, we ended up with an incompressible flow. Okay, this is so good so far, because it means that we can get a relation between incompressible flow properties and compressible flow properties through this mapping relation, through this transformation. However, we need to make sure that we are still talking about the flow around the same shape, the same airfoil. Okay, so to check that, we can check the wall boundary condition. If we have the same wall boundary conditions in both domains.
Okay, so did you see just what happened?
Yes, we basically get the Laplace equation for the new domain.
So with the magic of mathematics, now you ended up with the Laplace's equation, right? With the magic of mathematics. So of course, the variables are different, right? The variables are different. The dependent and the independent variables are different. Phi bar is not equal to phi hat. And eta, for example, is not equal to y. Psi is equal to x, but eta is not equal to y. So, but written as phi hat and written with the parameters, dependent parameter phi hat and independent parameters psi and eta, this equation, which is, I mean, mathematically, it is indeed Laplace's equation. It does represent the same physics. And the physics that we're talking about is the compressible flow around an airfoil in reality. I mean, after this transformation, I mean, the physical representation actually does not change, still compressible flow. However, so it also tells you, for example, the solution that you get, I mean, we know how to solve Laplace's equation in general, but if we solve this equation with these parameters, so it is, you know, it's very much related. It basically, since the incompressible flow is governed by the same equation, but different parameters, so they must be related. That's what we are trying to do. And I mean, the solutions must be related. The solution of incompressible flow and the solution for compressible flow, but that we obtain from this phi bar equation, they must be related to each other. So what is that relation? Because if the solutions are related, for example, pressure coefficient is a solution, is one of the solution parameters. So Cp value that we obtain from incompressible flow must be related to the Cp value that we obtain from this equation. They must be related. So what is that relation? So that was what Prandtl and Glar was after. That's why they call it compressibility correction, because again, I'm repeating this, the idea is to obtain a solution for incompressible flow and finding out this relation, which is called correction here. Using that correction, estimate the value for the, I'm using the result of the incompressible flow, estimate the value for the compressible flow. So that's the main ultimate goal or ultimate objective here. It's theoretical, as you can see, very much theoretical. So, but it does have a good amount of Mach number range that we can apply this correction. We will see, as it's said in the video, up to about Mach 0.7, the results of these corrections is very well applied, which means that, and it's actually quite a simple equation, that correction. You don't need to solve any equation for compressible flow. You just obtain, for example, Panel method solution up to, if it's up to Mach 0.7, you just multiply it with a correction factor. You get the Cp value for the compressible flow. Anyway, we will all see now in a second. Let's continue.
To make sure that we are still talking about the flow around the same shape, the same airfoil. Okay, so to check that, we can check the wall boundary condition. If we have the same wall boundary conditions in both domains, it means that we are working with the same airfoil in both domains. So let's start looking at that. So airfoil shape was defined in the physical domain as y equals to some function of x, fx. And then in the transformed domain, let's define eta as a function q of xi. So the linearized boundary condition, you may remember that we actually looked at this previously, in the physical domain is defined as tangent theta equals to df over dx. And v infinity times df over dx, which is, as you may remember from the previous slides, d phi hat over dy, and we also got this relation d phi hat over dy equals to d phi over bar over d eta, which means that in the transform domain it corresponds to this. Okay, now let's look at the flow tangency condition in the transform space by looking at dq over dxi term, and dq over dxi term in that case would be equal to d phi over bar over d eta. Of course, v infinity times dq over dxi term equals to del phi over bar over del theta. Okay, so it means that these both terms are equal to each other, which also means dfx over dx equals to dq over dxi, which means that we have the same flow tangency condition in both domains, in both physical domain and the transform space, transform domain, which means airfoil shape remains unchanged in the transform domain. So what we do then is we simply transform the compressible flow over an airfoil to an incompressible flow without changing the airfoil shape. So this also now justifies that this mapping, this transformation gives us a good relation between the incompressible flow over an airfoil and the compressible flow around the same airfoil. That's a good conclusion for now. Okay, now let's check the pressure coefficient. Now in the physical domain it was derived as shown here. This pressure coefficient was equal to -2 times u hat. That's actually the perturbation velocity in x direction over v infinity, or we can represent it in terms of the velocity potential phi hat, which is -2 over v infinity times d phi hat over dx. And now we can actually use previously achieved relation such that this d phi hat over dx is equal to 1 over beta times d phi over bar over dxi. Okay. This was achieved through this definition of the new potential field. Okay, let's come back to here. Then if I insert 1 over beta times del phi over bar over del psi here, then also replacing this with the perturbation velocity in the transform space, which is then u over bar, then I end up with -2 over v infinity times u over bar divided by beta. Of course, this u over bar is the perturbation velocity in the incompressible flow, because that's defined in the transform space as a function, as a derivative of perturbation velocity potential with respect to psi that corresponds to kind of horizontal axis in the transform domain. Okay, so knowing that, and also we can now equate Cp0, which is the pressure coefficient in the incompressible flow, to -2u over bar over v infinity. Then we get this relation, Cp equals to Cp0 divided by beta, and we know that beta is square root of 1 minus mach infinity square. Then your compressible pressure coefficient equals to your incompressible pressure coefficient divided by some factor, and that factor is 1 over mach infinity square. So this is known as the Prandtl-Glauert compressibility correction, which means that if you know the incompressible pressure coefficient for a point around an airfoil, which means that this has to be, a pressure coefficient that's lower than Mach number 0.3. Then if you want to calculate the pressure coefficient in a compressible flow regime, or for a for a higher Mach number, but that Mach number should be still smaller than 0.7, then you can get the pressure coefficient in incompressible flow by using this relation. So as you can see, there's just the compressible flow pressure coefficient differs from the incompressible flow pressure coefficient by just this factor, square root of 1 minus Mach infinity square. So if that's the case, as also CL and CM are kind of integrations of pressure coefficient or over the airfoil surfaces, we can safely write down these relations as well, because again the pressure coefficient differs only by a factor here, and then likewise lift and moment coefficients also differ by the same factor, as they are integrated quantities of pressure coefficient around the airfoil. Okay, now we have this compressibility correction, which is quite actually simple to use however, you should keep in mind that it's only valid for thin airfoils at small angle of attack, because we had the assumption that the perturbations have to be small, and it's only valid for subsonic flow and particularly for Mach numbers smaller than 0.7. Okay, there are also some improved compressibility corrections like Karman-Seen rule or Lighton's rule, and in these corrections you again have the incompressible pressure coefficient and some factor that's a function of Mach number as well. In Lighton's rule you also have the gamma value here in the denominator in addition to the Mach infinity square. Okay, let's look at how these compressibility corrections work when compared to some experimental data. Here are some wind tunnel tests on NACA 4412 airfoil at some angle of attack, and here the dots represent the experimental data, and the lines here represent different correction results, different compressibility correction results. Here the lowermost one is a Prandtl-Glauert one, and then we have Karman-Seen and then Lighton's corrections. As you can see, Prandtl-Glauert correction method underpredicts the results, and particularly it weights a lot at relatively high Mach numbers, as you can see here. However, the improved correction factors give slightly slightly better comparison when with respect to the experimental data.
Any questions? No questions? Okay, let's give a break then, and let's meet again at 2:40. Okay. Okay, so what we will see next is kind of an extension of what we learned so far. I mean, we learned basically the airfoil. Let me share this regarding what's happening to airfoil aerodynamics, but the correction and the linearization of the potential equation and the relation of its solution to incompressible flow solution, we have seen that, and therefore the Prandtl-Glauert correction. But the problem is this is, as you can see, it's quite valid, and the new versions of the correction actually, which you have seen that they work a little bit better actually. Prandtl-Glauer correction kind of under predicts CP. I was expecting you to ask a question at that point, but nobody asked it when we were showing the experimental versus theory or the correction method proposed for CP. I was hoping that you could ask CP at which location, right? It was just CP, experimental CP versus theory, but CP at which location? You did not ask that question. Anyway, so that was for knockout 4412. It's about 1 degree angle of attack. I think it's CP, since CP is a local parameter, that value is most probably the minimum CP level. So where we have the maximum suction, or at the suction peak, we call it. Most probably it's that CP. But anyway, what happens is that those methodologies that we just discussed in the previous hour, as we have seen in the video, are valid for Mach numbers less than 0.7. Why is that so? The problem is when the flow or the free stream Mach number, M infinity, reaches to certain levels, let's say more than Mach 0.65, Mach 0.7, the flow physics on the airfoil starts to change. And this region, in fact, we have a special name for this region, which is the region between Mach 0.8 and Mach 1.2. We call it the transonic flow region, transonic. The flow physics in this region is quite complicated, and in this region, the physics is also quite, somewhat different than what we have seen so far. When Mach, what we have discussed so far, the linearized potential flow theory and the corrections and everything are valid up to Mach 0.7, means that M infinity is about maximum, is about Mach 0.7, and the flow is entirely subsonic everywhere. So it is compressible, yes, it is compressible, but it is entirely subsonic around the airfoil. Nowhere on the airfoil the flow ever becomes supersonic. So the theory is valid under that condition. However, of course, this is not always the case. The thing is, first of all, what we do know is, and it will be explained in more detail in the video, is, depending, at some M infinity level, we know that, for example, on the upper surface, the flow will accelerate. And so the pressure will drop and everything. So static pressure, that is. So because of that acceleration of the flow, what if the flow accelerates so much that over the airfoil, it becomes locally supersonic? Okay, so that's a problem, because now if it becomes locally supersonic, what will happen downstream of it? Will it end up with a shock wave? Are we going to end up with a normal shock wave? Are we going to have an oblique shock wave? What will happen there? So, all these questions are quite valid questions. So this means that the flow behavior will be, first of all, mixed, meaning that we will have a subsonic and supersonic mixed region over the airfoil with possible shock waves occurring. So that's the main reason why I said the flow physics is going to be different. And that occurs when we reach what we call a critical free stream Mach number. After this critical free stream Mach number, the flow, or let me put it this way, at the value of this critical free stream Mach number, the flow reaches the sonic condition some point on the airfoil, and the most probable point is the minimum pressure location or maximum suction location. The flow will reach sonic condition. if the M critical is a subsonic value, don't get confused. As you can see here, M critical is, for example, 0.61. At that condition, for this given shape of this airfoil, and of course, this critical Mach number totally depends on the given shape. Somewhere on this shape, at this maximum suction point, most probably, it will reach sonic condition. If you're flying faster than this critical Mach number, you will end up with having a pocket of supersonic flow over the airfoil. So that's quite complicated region. So now we're going to learn this, which we call the critical Mach number. So let's start.
Chapters or sections we covered, we actually derived a linearized theory that's applicable in compressible subsonic flows, but you may also remember that I said at some point this linearized theory is not valid between the Mach numbers, free stream Mach numbers 0.8 and 1.2, and this range of Mach numbers is also known as transonic flow regime. Transonic flow regime by its nature is complicated and non-linear. Therefore, such a linearized approach, such a linear approach, does not work in this Mach number range. And in this section, actually, we are going to have a qualitative perspective in transonic flow regime from several aspects. So today's discussion actually is the critical Mach number, and let me try to explain what the critical Mach number means. So say we have an airfoil of an arbitrary shape, and we have a point on the upper surface of the airfoil, and this point is no arbitrary point. It's actually the point where the minimum pressure occurs. So at this point, well, of course, if you consider the free stream Mach number, let's start with Mach number 0.3. Then the flow first stagnates at the front side of the airfoil, and then it starts accelerating. And at this minimum pressure location, we reach to some higher Mach number than the free stream Mach number, as you can see here. So the free stream Mach number is 0.3. However, at the minimum pressure location, we have approximately 0.44 Mach number on the upper surface. So as the free stream Mach number increases, also the local Mach number that's obtained at the minimum pressure location increases as well. For instance, at 0.5, we have a local Mach number of approximately 0.78, and now let's even increase the Mach number a step further, such that we have 0.61 free stream Mach number, and at this very Mach number we have Mach number of 1 sonic speed at the minimum pressure location. So this Mach number, which actually yields sonic speed at the minimum pressure location, is known as or defined as the critical Mach number for this airfoil. And if you even further increase the Mach number, then above the critical Mach number, then you will end up with a sonic line where Mach number is 1, and within the sonic pocket you have Mach numbers greater than 1 here. So the estimation and the study of critical Mach number is quite important, because well, you may have a sonic operation of flight speed, subsonic operation of flight speed, as we have here 0.65, but over your wing you may have supersonic velocities, which as I'm going to explain in the coming section, which results in significant increase in drag. So for this reason, we need to have a knowledge of the critical Mach number during the design process. Okay, so let's look at how we.
Is the critical Mach number for any airfoil defined in the zero angle of attack situation?
Good question. Actually, it changes with angle of attack. Right now, for initial introduction purposes, we are discussing at zero angle of attack. But however, as you very well know, as we increase the angle of attack, the value of the minimum pressure changes. So the amount of acceleration also changes. So the angle of attack, it does influence the critical Mach number. In fact, for higher angles of attack, at the minimum suction location, we would have higher, let's say, Mach numbers. So basically our critical Mach number gets reduced at higher angles of attack in reality. Okay.
Thanks, sir.
Good question. Let's continue.
We can actually obtain or have a first estimation of the critical Mach number. So let's consider the critical case where we have some 0.61 Mach number and the local Mach number at point A is 1. Let's try to find out without considering or without actually taking into account the critical case. Let's try to obtain the static pressure ratio between point A and the free stream, which is PA over P infinity, as you can see here. So first of all, we may actually represent it in a form shown here. In the denominator we have PA over P0, which is the local static pressure in ratio to the total pressure, and here P infinity over P0 is the static pressure of the free stream static pressure divided by the total pressure in the free stream. So at this point we can assume that the flow is isentropic because, well, we neglect the effect of viscosity. We don't have any shock waves here, and we assume that the flow is adiabatic. So then we may assume that the flow is isentropic, which means then first of all these P0s are actually equal. So P0 in the free stream and P0 at locally around point A are the same, and we can also use the isentropic flow relations in order to have these ratios. So once you plug in the isentropic flow relations, we actually end up with this equation. And previously we actually represented the pressure coefficient in terms of Mach number, as shown here on the right hand side of the slide. So if I substitute PA over P infinity term here with the corresponding expression here, I end up with this final equation. This equation is an important equation. It actually tells you the relation between the pressure at point A and the velocity at point A, as you can see. So you can actually consider this as a kind of corresponding expression for a Bernoulli equation in the compressible flow. So of course Bernoulli equation applies in incompressible flow. It also gives you the relation between pressure and velocity locally at a point, and here we also have a similar relation. For point A we can have the relation between velocity and the pressure. Okay, but we are interested in the critical Mach number. So we are looking for the Mach infinity value that will actually give us some sonic speed, that will give us sonic speed at point A at the minimum pressure location. So then if we would like to have Mach number 1 at point A, we can actually replace this MA term with 1. Then we can replace Mach infinity term with Mach critical, and then in that case the pressure coefficient we will obtain would be critical pressure coefficient. And finally, by doing all these substitutions, we achieve this equation. This equation is an exact equation. It's not an approximation. It's for isentropic flow. Under the isentropic flow assumption, it gives us the critical pressure coefficient at the minimum pressure location, or, well, you can actually consider at the location where we have Mach number 1. It doesn't have to be the minimum pressure location, but it's the it gives us the pressure coefficient wherever the Mach number is equal to 1 on the airfoil in relation to the free stream Mach number. Okay, And well, this is an exact expression. On the top of that, however, it doesn't actually contain any information regarding the airfoil. So it's for an isentropic flow between free stream flow and also a point in the flow. Okay, so we need to also combine this with some airfoil information in order to find the critical Mach number for a given airfoil. So here the steps are actually summarized in order to find or calculate the critical Mach number. First of all, let's go step by step, and I will show you how it's actually done. We know that the point A is the minimum pressure point over the airfoil. Okay, so we first need to find the minimum pressure value in the incompressible flow. So we start with the incompressible flow over the airfoil at various Mach number Mach infinity values, free stream Mach number values. Okay, so at minimum pressure location, you may use a kind of theoretical approach or empirical or experimental approach in order to calculate the pressure coefficient at the minimum pressure location for an incompressible flow. Now we have for very low speeds, we have some pressure coefficients now over the airfoil. Now, of course, we can only assume that flow is incompressible up to some Mach number, but that's actually specifically 0.3. But above that, we need to take into account the compressibility effects. So, what the good thing is, in the previous section, we developed Prandtl-Glauert compressibility corrections, but there were also some improved methods of correction. You can actually use one of them in order to correct the CP values at the minimum pressure location and actually plot it. So you need to plot minimum CP value at the minimum pressure location, corrected values, versus Mach infinity values for a given airfoil. Okay, because what you are doing up to this fourth step is completely related with the airfoil, and it will change from airfoil to airfoil. Okay, then you need to also plot this CP critical versus Mach critical curve, okay, using the expression that's shown here. Now, the intersection of these two plots will actually give you the critical Mach number, and it's actually schematically shown here. So this is actually the exact expression we derived. So for changing Mach critical values, what should be the corresponding critical pressure coefficient at the minimum pressure location? Okay, and this curve is just an approximation because we are using some compressibility correction. We start with incompressible pressure coefficient, and we apply corrections, and then we end up with this curve. And intersection of these two curves gives you the critical Mach number for the airfoil, which you use in order to calculate, this variation of minimum pressure coefficient. Well, of course, it changes from airfoil to airfoil. Here we have two examples. Again, this is the exact curve, expression, and here you have a thick airfoil and a thin airfoil. And of course, thin airfoil generates very small perturbations in the flow. So you may remember that we showed the relation between the pressure coefficient and the perturbation velocity in the x direction. So because thin airfoil results in smaller expansion of the flow, as well as which results in smaller perturbation velocities, it has some small values in magnitude in the pressure coefficient, as you can see here. However, thick airfoil really perturbs the flow, and as a result you have larger magnitude minimum pressure coefficients for the thick airfoil. And then if you look at the critical Mach numbers for these two airfoils, you can see that the critical state is reached for the thick airfoil at much smaller Mach numbers than for a thin airfoil, because thick airfoil perturbs the flow a lot, and it results in it results in, you know, achieving larger Mach numbers on the upper surface when compared to thin airfoil, which is actually shown here. So you have a sonic speed for a thick airfoil at much earlier, at much smaller Mach number than that for a thin airfoil.
Okay, so let me ask you guys a question at this point. So let's say, I mean, this plot is for a thick airfoil versus thin airfoil. I guess you understand, you may understand what happened here. A thick airfoil will end up with a lower M critical value because of the fact that at the same, and assuming that they are both operating at zero angle of attack. Yeah. Simply because of the fact that thick airfoil creates a bigger disturbance. At the same M infinity, thick airfoil will reach the supersonic or sonic condition on top of it earlier. So let me ask you a question related to this. Let's forget about the thick airfoil. Let's say we have only thin airfoil. So we have the lower line here. So we have thin CP0, thin airfoil crossing the CP critical equation in terms of M critical, and that cross-section point we have M critical for thin airfoil. Let's say I have the same thin airfoil but operating at a higher angle of attack. Okay, what would happen? I mean, I said that a few minutes ago, angle of attack has an effect, and it will change the critical Mach number. How would you expect this curve to shift? That's my question.
Hocam, it would behave like a thick airfoil.
Mm-hmm.
The M critical will decrease, I guess.
So you're right. So what will happen is M critical will decrease because, I mean, why does it decrease? That's why I'm asking. It decreases because the thin airfoil curve that you are seeing here, right? This curve will shift towards left, basically, on this CP critical line. Why? The main reason is that this CP0, this thin CP0, this is our starting point. Yes, this is obtained from the incompressible flow theory, and we then correct it following this line. This CP0 will be different if the airfoil is operating at an angle of attack. This CP0 will be actually more negative, so therefore actually less, and you can see this x is negative. CP is a standard usage in aerodynamics. We generally show reversed CP axis. So if you go up here, it's more negative. So CP0 at an angle of attack will be more negative. So this curve will shift. I mean, this thin CP0 will have a value upper in this axis. So therefore, if you follow the correction line, it will cut it at this point. Similar to thick airfoil, it will have a lower M critical value. Yes? Did you get this point? I guess you got it. Let's continue.
Hocam, can I ask something?
Yes.
The behavior of thin airfoil curve won't change, right? It will just be shifted up in CP minus axis.
That's right, because the behavior of the curve is the correction equation.
Okay.
In the correction equation is just CP0 divided by square root of M minus M infinity square. But the only thing that will be different in that equation will be the CP0 value. Yes?
Okay, hocam, thank you.
Mm-hmm. Good. Let's continue.
Okay, so I would like to give you final some notifications about this critical Mach number. First of all, you may actually ask this question: is the minimum pressure location corresponds to maximum thickness location The answer is no, which you can actually see it for yourself. For NACA 0012 airfoil, the maximum thickness location is about 30% of the chord length. However, the minimum pressure location is about 11%. So 11% of the airfoil. So you may actually intuitively think that the minimum pressure occurs at where the maximum thickness is, but it's not actually locally working that way. You need to consider the complete flow field around the airfoil. It's not, you cannot just locally assess the situation. So the other question you may ask is, okay, is this, we start with incompressible minimum pressure location value, pressure coefficient value, but is it the same if you move to higher Mach numbers? Well, you can actually see it also here. So this is the incompressible case, and these two are for larger Mach numbers, and for all of them the minimum pressure location stays about 11% approximately. It changes, but it's not that much. Okay, thanks for listening. I will continue with the coming presentations.
Okay, let's continue with the next video.
Hocam,
Evet.
we are talking only with the upper surface, right?
Yes.
In the lower surface, the effects are reversed once angle of attack increase.
In the lower surface, pressure coefficient will not be as low as the upper surface, first of all. So therefore, the Mach numbers will not be as high as the upper surface. That's the main reason. Okay.
Okay, so thanks.
Let's continue with this.
Hello everyone, this is Dr. Mustafa Perçin again. Today I'm going to continue with our discussion on compressible flows over airfoils. Well, particularly I'm going to talk about direct divergence, Mach number, area rule, and supercritical airfoils in this presentation. So, well, you may remember that when I was talking about critical Mach number, I was telling you that this critical Mach number is an important parameter in the design process, because above these critical Mach numbers, one can actually observe very significant increase of drag coefficients. And for this reason, you need to pay attention, or you like to have critical Mach number as high as possible in order to extend the range of Mach numbers that your aircraft can fly. Okay, so let's have any airfoil, and let's do an experiment in a wind tunnel where you have the airfoil at a fixed angle of attack, and we step by step increase the Mach number and see how the drag coefficient changes. And this plot actually represents that. So this is CD versus Mach number, free string Mach number plot. Okay, at very low speeds, you would actually have this incompressible drag coefficient, which is indicated here, and for some range of Mach numbers, so from point A to C, you would actually see that this drag coefficient does not vary too significantly. So it's rather constant actually in this range. And this point C corresponds to critical Mach number here. So this is the Mach number where you actually see when you actually see at a point at the minimum pressure point Mach number 1 on the upper surface of the airfoil. Okay, let's increase the Mach number slightly to point D, and then at this point you would actually see a small supersonic flow pocket or bubble on the airfoil surface, where the Mach number can reach values from 1.02 to 1.05, and the drag value slightly increases. So let's increase it to even further, to point E, and then you would actually see that from this point E on, you have a significant or dramatic increase in drag coefficients. So actually, the Mach number where the significant increase starts is defined as the drag divergence Mach number. So let's see what happens in this case. over the majority of your airfoil surface, then in this case you have a supersonic flow. So you can actually observe 1.2 to 1.3 Mach numbers, 1.2 to Mach 1.3 in this case. And this supersonic flow is terminated by shock waves, both on the above and the below surfaces of the airfoil, upper and the lower surfaces of the airfoil. This shock wave generates an increase in the pressure, static pressure, that results in an adverse pressure gradient, and that eventually leads to flow separation. Okay, this flow separation results in a significant increase in the drag coefficient. Okay, so therefore this drag divergence Mach number is an important parameter for an aircraft, as you can see. But what happens if you get close to Mach number 1? That's actually a kind of question you may actually pose here. So free stream Mach number 1 you can actually refer to as the sound barrier. So as you can see, it increases. And if you look at the Prandtl-Glauert compressibility correction, you may already remember that as your Mach number gets closer to 1, this pressure coefficient value goes to infinity. It's already evident from this equation that there is something happening. There's something happening as you get close to Mach number 1. Well, you may actually ask this question: is it really getting? Shall I have really an infinite pressure coefficient as I get to Mach number 1? Well, fortunately, no, because this you may remember this Prandtl-Glauert compressibility correction is a kind of linear theory based approach, and it's not valid actually in the transonic flow regime. That's why you cannot use this correction here, but this correction already hints that there will be some sharp increase, or there will be some non-linearity as you get close to Mach number 1. Okay, so then what happens as you get close to Mach number 1 here? So at Mach number 1, which is referred to as the sound barrier, you have a peak in drag coefficient, and then as you move to the supersonic flow regime, as you get Mach infinity larger than 1, it starts decreasing again. So then what you need in order to really really have a supersonic flight, you really need to have a strong engine that can generate enough thrust to overcome these large values of drag, and particularly at Mach number 1, where we refer to as the sound barrier. So if your engine is strong enough, powerful enough to overcome this drag, then you can actually move into the supersonic flight regime, where the drag coefficient value starts decreasing again. Okay, so well, what can you do about this in order to improve this situation? Let's look at this. First of all, it would be desirable to have a critical Mach number as large as possible in order to extend the range of Mach numbers that you can actually fly. Because if you delay the critical Mach number, if you increase the value of the critical Mach number, the direct divergence Mach number will also increase because it comes after that. Okay, that's actually one way, and the other way is to decrease this peak value of drag coefficient, which will allow you to overcome or go over the sound barrier with relatively less power requirements. Okay, for the first case, I mean, in order to delay this critical Mach number, you can actually use a thinner airfoil, right? Because I showed you earlier, thinner airfoils, because they generate less perturbation in the flow, would have a larger critical Mach number, and as a result, direct divergence Mach number for a thin airfoil will be also higher. But for the second case, let's look at what you can actually do. So there is this area rule, and I will try to explain it by two sketches I'm going to show in the coming 2 slides. So rather than looking at the cross section of an airfoil of the wing, let's look at the cross section, which is actually here the BB cross section, and the area of this cross section as we move in the x direction over the aircraft. Okay, so we take a section at every x location, and we look at the cross section area value, and we plot it here. Okay, that's the plot you would have. So this is a non-area ruled aircraft. Well, it was already known in the field of ballistics that in the field of ballistics that supersonic bullet or artillery shell with a less with a smooth variation of cross-section area has better properties than those which have more abrupt changes in the cross section. So that's actually what we observe here. So this is a non-area ruled aircraft, and as you can see, as you move from fuselage to the wing area, there is like an abrupt change, and as the wings end, then you have a sharp decrease again in the cross section area. But on the other hand, if you look at look at this aircraft, where you actually have a narrower fuselage in the region where your wing actually starts to increase the cross-section area, then you would actually have a more smooth variation of the cross-section area. And then if you look at the drag coefficient comparison for these two aircraft, you would actually see that the one with an area rule has a smaller peak value at Mach infinity 1 when compared to the without area rule case. Okay, so then this is already an important let's say rule of thumb when you are at the stage of designing an aircraft. So try to have smooth variations of the cross section area, particularly if you are planning to fly at sonic speeds or at in transonic regime or in the supersonic regime. Try to have smooth variations of the cross-section area as much as possible. Okay, so this actually decreases the peak drag coefficient value that you would actually observe at Mach number at free stream Mach number 1. Well, on the other hand, I was telling you about delaying.
Okay, let me tell you a few words about this. Maybe we'll watch some videos also. The thing is, flying supersonically was a big challenge. I don't know if how familiar are you with the history of this. I mean, after the invention of jet engines during the Second World War, of course, aircraft started to fly faster and faster. However, for a long time, people believed that supersonic flight is basically impossible. Basically impossible, because that's why actually they refer to as sound barrier or sound wall or something like that. People meaning scientists working in this field, not people, everyday people, believed that this was impossible to do. But later, after the understanding of the physics better, meaning that the understanding of critical Mach number, understanding of the sudden drag rise that is happening, and why this drag rise is actually happening, of course, after putting in a lot of effort in wind tunnel tests and in the theory of aerodynamics, people understood why the drag rise was happening. And then once it was understood, scientists and engineers started to propose solutions, engineering solutions to aircraft design, so that this can be overcome, meaning that aircraft now can indeed fly in supersonic speeds, so faster than the speed of sound. One of the we have seen two solutions so far. The first solution is very straightforward: use a thin airfoil. Okay. Use a thin airfoil to push the critical Mach number to higher Mach numbers. And the second solution we have seen is what we call the area rule. So area ruling an aircraft indeed helps reducing the maximum drag that occurs near the sonic condition. The third solution is right now we are discussing the usage of supercritical airfoils. So whatever that is, we will see. And the fourth solution is actually using a sweep angle when we are designing wings. So we will also talk about this. Okay, and of course, at the end of the day, you have to do all four of these. Plus, you need to have a strong or powerful propulsion system to push you through this high drag region. Okay, and only after that. you know, people or engineers started to come up with fighter aircraft, especially that can fly at higher supersonic speeds. So there are certain examples. For example, this area ruling was not known, and there are certain example aircraft. If I remember correctly, it was F102. F102. When it's an old, you know, it's an old era delta wing aircraft. When it was first designed, it was not area ruled. It had very much difficulty flying supersonically. Then later versions of it, it was area ruled, and it was easy to. It was relatively easy. It could fly supersonically. I will maybe show you some pictures and videos about this later. Let's continue.
This critical Mach number, and then I told you that thinner airfoils have higher critical Mach numbers. However, there are also some other let's say aspects that you need to take into account while designing an aircraft. Well, you cannot actually make the airfoil infinitely thin or very thin and then expect that it will still operate at the given flight conditions, because you need to consider the structure from structural point of view. Is it rigid enough, or you need to also have some space probably for some storage or fuel. So in this case, you cannot actually make the airfoil too thin. So then well, it's actually also written here. Then you need to have well, some other solution for that if you want to increase the direct divergence Mach number. And one solution is using supercritical airfoils. So in this case, we are actually not increasing the critical Mach number by use of supercritical airfoils, but this solution is actually allows or results in increasing the direct divergence Mach number. So you may still have similar critical Mach number, but the distance between critical Mach number and the direct divergence Mach number increases by use of the supercritical airfoils. Okay, let's have a look at two different airfoils shown on this slide. One of them, NACA 64 series airfoil, and these NACA 64 series airfoils are kind of laminar airfoils, so they are designed for low-speed flights. But in the past, it was recognized that these airfoils have relatively high critical Mach numbers. Therefore, they would also have relatively high direct divergence Mach numbers. So therefore, they were used in the first versions of transonic supersonic flight, supersonic flying aircrafts. However, of course, they are not still tailored for this flight conditions. And on the right hand side, you see a supercritical airfoil, and this has 13.5% thickness, and it has a more flat upper surface compared to kind of standard 64 series airfoil. Let's look at the differences, and below you can actually see pressure coefficient variations for the upper and the lower surfaces. The first difference is that in the case of supercritical airfoil, the supersonic flow region is more limited, or is closer to the upper airfoil surface, whereas for the 64 series, it's actually extended more in the upward direction, as you can see. The other difference is that the magnitude of the pressure coefficient, negative pressure coefficient on the upper surface, is much higher in the case of NACA 64 airfoil, whereas it's much lower. It's much lower actually in the case of supercritical airfoil. You can actually consider this being a result of having less perturbation in the flow because of the flat upper surface compared to 64 series airfoil, where the perturbations are slightly higher. And on the top of that, the Mach numbers that you would actually observe on this flat surface would be smaller than the Mach numbers that you would actually observe here. So as your Mach number is smaller in this case, you would actually see a relatively weak shock wave in this case, as you can see here. Well, because Mach numbers are greater in the 64 series airfoil, you would have a relatively strong shock wave, but in this case you would have a relatively weak shock wave because Mach numbers are smaller in the supersonic flow region. Okay, let's look at how this actually affects our drag divergence Mach number. As you can see, this is for NACA 64 series airfoil, where your drag divergence Mach number is about 0.67, but if you move to supercritical airfoil, your drag divergence Mach number is definitely higher. It's about 0.79 or 0.88, let's say. Okay, so as you can see already from this example, drag divergence Mach number increases when you use supercritical airfoil. But let me give a short notification about this cusp shape of the supercritical airfoil. Because you have a flat surface here, you have actually a negative camber in the first probably 60% of a supercritical airfoil. That decreases the lift coefficient. That's why closer to the trailing edge, the camber value is increased in order to compensate for the lift loss in the front part of the airfoil.
Okay, great. So we are right on time. So let's stop it here, and we will continue with one more topic related to this tomorrow. Okay, any questions?
Hocam, about that area distribution of area ruled aircraft, why is it like it doesn't change in X? I didn't understand that part, I think.
I mean, when you plot the cross-sectional area of the aircraft, right? Normally, what the area rule states that you should not have sudden dramatic changes in the area. The best way to have reduction in the drag coefficient in terms of transonic conditions is to have a smooth area variation like the one that you are seeing here. So basically, if you do not have, you see the fuselage shape is like what they call in the old times. This was realized during 1950s. So in 1950s, Coke bottles, Coca-Cola şişeleri, they had this thin belly, right? İnce belli, right?
Yes.
So what you do is, instead of having a thick fuselage here, and with the addition of the wing area, you suddenly end up with a sudden area increase. Instead of doing that, as the wing gets into the picture, and the wing is trying to increase the cross-sectional area, you reduce the cross-sectional area of the fuselage to compensate for it. Okay, so at the end, you end up with a relatively smoother distribution of cross-sectional area along x-axis.
Okay, hocam, I understand.
Mm-hmm.
I understand.
That from wind tunnel tests, people realize that having this kind of area distribution actually reduces your maximum drag coefficient at sonic conditions. So this was proposed.
Hocam, what is the physical explanation of this area rule gives us the better performance for the supersonic flight?
I mean, the physical explanation is related to, first of all, the pressure distribution again, and the shock wave structures occurring on the aircraft, especially upper surface of the wing. Okay, the strength of the shock waves and everything. But it does not, of course, only having an area rule doesn't help just by itself. You need to think about, as I said, I mean, the flow field is quite complicated. It's filled with all kinds of different shock wave structures. So by selecting proper thin airfoils, maybe also with supercritical airfoils, by area ruling and by sweeping the wing. As you can see here, we do have a sweep. Then only then we can, we have a controlled way of reducing the drag increase, which is mainly due to this sudden end of the supersonic pockets or supersonic regions that we have on the upper surface, sudden end of the supersonic regions with a strong normal shock waves. Okay.
Okay, so thanks.
Any other question? Okay, let's stop here and let's continue from this point tomorrow, okay? Herkese iyi günler. Yarın görüşmek üzere.
İyi günler hocam. Dikkat edin kendinize.
İyi günler. Teşekkürler size.